So we are ready to start. Next speaker is Branislav Jurco, going to talk about on the category of BB theories. Thank you.
Yes. Yeah. Okay. Good. Good. Is this switch on or?
Yeah. This.
Okay.
Top button is the pointer.
Yeah.
This is back and forth. Try to avoid these ones as they mess up with the presentation.
Okay. So just okay. Good. Yeah. Good. Okay. Okay. So first of all, thank to organizers. Okay. Yep. Good.
Small announcement. There are several of you who are asking for receipts of the fee that you paid. If Evgenia comes tonight, probably she will be with us in the Greek night. So tomorrow, approach her to get the same holds for those who came to me to pay their fee. So from tomorrow, she will be here, right?
Okay, so now we can really start with our speaker.
So let me first of all thank the organizers for this fantastic conference and for the opportunity to give the talk, and all the speakers before and after me for the nice talks. So my talk is about, well, you see the title, so I will not repeat it, but this is still some work in progress. So it will be kind of an introduction and motivation to, within maybe some outlook where we are trying to get or go. So these are my collaborators on that, Jan Pullman and Martin Zika. And okay, so well, let me just introduce some notation and well, some basics, some background. So what I will work with is differential graded vector space, or will be differential graded vector spaces, like this one V. For some technical reasons, I will assume that these vector spaces are degree-wise finite dimensional. So they are symplectic in addition to being differential graded. So we have an odd symplectic form of degree -1. Well, the differential will be denoted as Q, and the symplectic form and the differential are supposed to be compatible. Well, so that's the first slogan. Is that the solutions to quantum master equation on some odd symplectic differential graded vector space are one-to-one with quantum L-infinity algebras. So if you are familiar with quantum Batalin-Wilkowiski formalism, then essentially you know everything about L-infinity algebras and vice versa. Okay, so what is for me a solution to quantum master equation? Well, that's the standard thing, right? So I have an expansion in loops. Well, the G, the H bar counts the loops, and so right, and so this is sum of monomials in the fields, where it's written the way which makes it easy to translate into the language of L-infinity algebras or quantum L-infinity algebras. So the coefficients in these expansions, they are described by maps from symmetric power of my graded symmetric power of my vector space into my field. So let's say R, which are of degree 0, of course. So this is a typical element of the space of functions on my vector space. And so, well, I work with formal power series in H bar. Here E denotes a homogeneous basis of my vector space, and phi, the fields are dual, formed by dual basis. The free part, which is the quadratic part here with the G0, well, corresponds to the, is made of the differential and symplectic form, and the rest is interaction, which, yeah, at degree 0, it has to start from 3. I mean, in genus 0. Okay. Well, having this, we can construct, as usual, the Batalny-Volkovitsky Laplacian delta operator and the corresponding bracket. And, well, we extend it via linearity formal to the power series of H. Well, I will skip all these like details, technical details. Okay, so then quantum master equation, as you know, it just says that Batalny-Volkovitsky delta applied to the exponential of S is 0, and you can write it equivalently, well, either this way, where you immediately see that the part which would correspond to the classical Batalny-Volkovitsky equation, had it been no Batalny-Volkovitsky delta, or you can view it, if you like, the language of differential graded manifolds, homological vector fields. So it says that you have now a homological second order differential operator which squares to 0. Again, this would be the homological vector field, the Poisson bracket with the action, if we consider the classical, would consider the classical case. So now we can just translate this into the language of our coefficients here in the expansion, in these maps from the symmetric power of our vector space into the field. Well, just plug in and compare into master equation and just compare, you know, the according to the genus and coefficients according to the genus and a number of inputs. And well, you get the expression. So these are some algebraic relations for these coefficients in the master action, which are equivalent to, yeah, to the quantum master equation. Again, you see piece which comes from quantum, from loops, from Batalny-Volkovitsky delta. This is this one, where you kind of self-contract the inputs of these f's, and well, that would be the classical part of a cyclic L-infinity algebra. So if you forget about G, you get a cyclic L-infinity algebra and the solution to the classical master equation. So this is how the equivalence goes. Since maybe you like better the language of operations, if you know L-infinity algebras, then you think of them also as maps which have, let's say, n-1 input and 1 output. So here you can go to this. Since your symplectic form is non-degenerate, you can use these coefficients in the expansion for the master equation, for the master action, define these operations. Well, unambiguously. So you end up with these maps as you are used now of degree 1. And you can rewrite the relations for f's in terms of these operations, if you like it better. Okay, now I forget about H from now. So if you like H, you can put it in wherever you think it's appropriate. maybe I's also. I already from the beginning didn't write I in the front of the action. Okay. Now the correspondence goes further, and kind of another type of relation we have is that on the side of Batalin-Wilkowiski theory and quantum master equation, well, of course, we compute, let's say, S matrix, do perturbation theory. So we do Batalin-Wilkowiski integrals. And here on the homotopy algebra side, we can do homological perturbation lemma. And these things, again, are kind of equivalent. So here, what you compute is the S matrix, whereas here what you get is the minimal model for your L infinity algebra. This means that you get a quantum L infinity algebra on the cohomology of Q of the free BRST operator. And even more, this tells you that you have a decomposition theorem, that you can decompose any quantum L infinity algebra in the minimal one without differential, but all other operations non-trivial, and the contractible part, which has only differential, and all the operations are higher operations are trivial. So how does it work? Let me remind you. So associated with our differential graded vector space or symplectic one, we always can construct the so-called Hodge or maybe harmonious Hodge decomposition. So you can split your vector space into the cohomology of the Q. And so now, and in a symplectic complement to that, so H itself inherits the symplectic structure from the vector space V, and it has a symplectic complement, which splits into pieces which are Lagrangian here inside. And the differential acts non-trivially only on this piece, on which I denoted C. So B is image of Q. And then you have the partial inverse, the contracting homotopy, which goes the other way around. Well, so the statement is that you can always do that in a way that your contracting homotopy is also compatible with symplectic structure, and hence the cohomology inherits the symplectic structure, and also this, well, this is, as I said already, symplectic complement. And correspondingly, you get split well, it will just remind you that since BV delta and Poisson bracket BV are made out of the inverse of omega, so obviously they will also split according to this Hodge decomposition into two pieces, one on the cohomology and one on the complement. Now, in my situation, I use only a particular case of homological perturbation and homotopy transfer. So what I have, as you see, is I have my starting vector space with differential Q. I have a projection to homology according to my Hodge decomposition. I have inclusion of the cohomology and this contracting homotopy. And of course, by construction, these P's and I's are maps of differential graded vector spaces. So they intertwine between this Q here and the trivial one here. Well, and actually, we are in a very special case where we can, well, which goes under the name special deformation rectract, where we have also these nice conditions for K, which is of course degree -1. It's partial inverse to something which is degree 1 to Q. And yeah, so the compositions with inclusion and projections are nice. And the important thing is, of course, that it is contracting homotopy. Okay, now I would like to go from my underlying vector space to my vector space of functions, of fields. And you can do this using the tensor trick, which goes, I don't know, back to Eilenberg, and I don't know, like. So you can construct, starting here, a special deformation retract on the functions, and well, you can induce the contracting homotopy K and the projection injection and Q, like lifting them using the tensor trick. Now, what I would like to do is to perturb my free BRST operator. I can perturb it in many ways, but for me, the one I like most is I just perturb it with Batalin-Volkovitsky delta. Well, if, as I said, if you like, you can insert here H bar, and it would make more sense. Then you can think of H bar as being something small and consider, well, this geometric series. So for me, that's just the perturbative expansion, which is conveniently written as a geometric series. So what the perturbation lemma tells me is that if I perturb the differential here, I get a new differential on the right-hand side, and I get a new special deformation retract again, where the new projection is made out of the old one and the contracting homotopy and delta using this geometric series. The same for the new inclusion, and the same for the new contracting homotopy. And well, the important thing is that again, these P and I's intertwine between the corresponding differentials. So what we see immediately that, if we compose delta plus Q with the new projection, that way it's the same as if we would first do projection and then just apply the Batalin-Volkovitsky delta restricted to the homology. And therefore, it tells us that whenever we start with an interaction part, which is the solution of the quantum master equation, they just, quantum master equation rewritten for the interaction. This is the free part is included in the Q. We immediately get a solution to the quantum master equation on the cohomology. Well, and this is how you get it, right? Using the projection, just written out explicitly. So obviously, well, what we get, we can call, for example, effective action, but since you get something on the cohomology, which means that you get a function on physical states, right? These are the physical states. And so there is no quadratic part, there is no propagator anymore. So it's kind of easy to believe that what you computed is actually the S matrix. Well, in the language of quantum field theory, it would be S matrix. In the language of homotopy algebra, that would be the minimal model for my Q infinity algebra I started with. And so the construction where you start with an action and produce the S matrix or effective action actually comes from a quasi-isomorphism of L infinity algebras. So it's, I didn't tell you what the morphism of quantum L infinity algebras is, but I'll come to that hopefully later. But when restricted to the cohomology, it is isomorphism. Also from perturbation lemma, we immediately have a decomposition theorem, because again, this is my new contracting homotopy, and I just apply the equation to the exponential of my action. And I see that my effective action, if I compare it to my starting action, the difference is exact in the, for this delta plus Q. And a little work just tells you that it follows immediately that you will find the canonical map on your symplectic vector space. Well, will be nonlinear and will be starting with identity, such that it preserves, I said it's a canonical map, it preserves the symplectic structure and just maps the semi-density, the original one, formed by the original action into the semi-density on the, well, for this decomposition of into the minimal model and the free action. And you can prove a little theorem that actually this is the same as what you would formally in quantum field theory write like this. So you take your exponential of the action, restrict it, so fixed gauge, so put everything which is in B to 0, so you get something which lives on the cohomology and on the Lagrangian submanifold in this complement. So this is a little difference. Normally you are used to integrate over a Lagrangian submanifold in the whole space. Here not. Well, the reason is obvious, because you don't have a propagator on H, and the Q is there 0. So you integrate over this isotropic subspace, and you end up with a function on the cohomology. And well, and you can compare the perturbative expansion of this integral and the perturbative expansion of the coming from the homological perturbation lemma, and you can do it, well, by some abstract reasoning, but you can also do it by hand and compare the combinatorics, and whatever you do, well, you will get the same. So I hope I convinced you that at least in the formal level, when the integrals are kind of finite, and I don't have problems with defining properly Batalin-Volkovitsky operator, the problem in the quantum field theory, but not with string field theory, for example. Well, what mathematicians did many years, for many years, and what physicists did, well, they did the same thing. Okay, so now just a remark that in both cases, either for the effective action for the S matrix or for this decomposition theorem, we always had a map which was a Poisson map, actually. So now you can ask, yeah, when I would consider two Batalin-Volkovitsky theories or two quantum L-infinity algebras to be equivalent, and of course there is a natural answer on the physics side if the S matrix is the same, for example. So, but let me maybe try to put it in a broad perspective and into most general setting as I can. Okay, so obviously we would like to have the minimal model to be equivalent to our starting action, definitely. And of course, also this action we've got as a sum of the free one and the effective action, which gives us the decomposition. Also this one, of course, we would like to be equivalent to our original action. Well, in this case, we had the field thread definition, we knew already. So, well, anyway, it is, since there is always this symplectic form around, we have to care for. We would like consider Poisson maps. Well, everything should be in some sense compatible with the symplectic structure. But you see, it's a bit too restrictive, because if you think about Poisson maps, they, with respect to dimension, they go only in one direction. So it becomes a bit non-symmetric, and well, I was not happy with that. So, so my question is whether we can do better. And so the motivation for what we might try to do is the following. So remember, in the minimal model, when we construct the effective action, so, well, always in Batalin-Wilkowiski, if you are familiar with, there is always the most natural thing to consider that these are half densities. So you, related to your action, you form this half density. Well, it's a nice half density because there is this exponential, and this is just the, I'm on a vector space, so this is just the, you know, the ordinary volume form on the, just the Lebesgue measure on the vector space, the unique up to etc. Translational invariant. And so you can consider, you remember in my Hodge decomposition of my vector space, I had the cohomology, and I have these two Lagrangian subspaces in the complement, which I used for the gauge fixing. So I was integrating over this C, and I can consider just this space. Okay, well, this is more manifold-like notation, because eventually I would like to generalize everything to manifolds. If you prefer having direct sum, please direct sum. Well, and I can think of a Dirac delta, which is supported as a density, half density, supported. You remember, my original model lives on V, my minimal model lives on homology, and it is easily to check that if you, I didn't write what it is, but so here I have a natural plus symplectic structure, which is this minus here means I take this one with the minus, so I have a difference of symplectic form. This is a symplectic form, and well, it's almost immediate that this is a Lagrangian subspace here. And so I take this half density here, I take my half density corresponding to the action, and well, I immediately see that if I multiply them, I get the density on V and the half density of H. So I can integrate this one over V, and I end up with a half density on the H. And the observation is that now you can rewrite your integral, giving you the minimum model or the Batalin-Wilkowiski integral, like an integral of e to s over the whole V, but restricted to this Lagrangian. Now really integrate over Lagrangian submanifold. And what I claim is you get the half density on the homology, which has the effective action or the minimal model. And so this was for the minimal model or for the S matrix for effective action. And for the, it's even easier for the decomposition theorem, because now we have these diffeomorphisms from diffeomorphism phi relating our actions. And this is obviously, the graph of this phi is obviously a Lagrangian here. So now you take delta distribution supported on the graph, and you integrate, and what you get is your action corresponding to the decomposition theorem. So you see some pattern is emerging. Well, it suggests that we have to look to something which you probably seen already, to an odd symplectic version of Weinstein's symplectic category. And okay, it's also an important thing which I should mention. All densities I introduced, okay, they are delta closed. In the sense, delta, Batalin-Volkovitsky delta, acts naturally on densities. So any density can be written in my case like a product of a function and the half density coming from the volume form, and the Batalin-Volkovitsky acts on the function and maps a half density into half density. And this works also for manifolds locally. This is this. Okay, I come to that later. So it is natural in this context consider the quantum odd symplectic category, which was introduced by Paulo Sciavara. So where the objects are odd symplectic, well, you can have even super manifolds. So you can have an extra Z. Everything works with an extra Z2 grading. And so morphisms would be generalized half densities on this product of the two symplectic manifolds, with the difference, with the symplectic structure given by the difference of symplectic structures. And so how you compose these things, you know, you have a half density here, you have a half density here. Well, you tensor them, you get the density on the middle on M2. So you can integrate over M2 and you get half density on 1M times, on M1 times M3. So that is Paulo's odd symplectic category. As I said, yes, exactly. This, well, yes. Okay. As I mentioned, this is this Kuda-Verdian definition of delta acting on semi-densities. And well, the proposition of Paulo tells us that in his quantum odd symplectic category, if you compose two delta closed morphisms, then semi-densities, you get again a closed semi-density or half density. So this is my preliminary definition suggested by the above. So if I have an odd symplectic manifold, first of all, okay, what is for me now a solution of a quantum master equation? It's a delta closed half density on it. And if I have two such odd symplectic manifolds with two such half densities, morphism between them would be some half density on this product, such that, again, delta closed, such that I compose F with rho, which means that I integrate over M. I multiply and integrate. I get the other half density. And what I showed you before, these are exactly the examples of this definition, the minimal model and the decomposition theorem. But now I made it again, you know, with correspondences, it became symmetric between M and N. But now this integration made it again kind of non-symmetric because I integrate, you know, one way. So I'm still not happy. So therefore, yeah, we work now on improved version of that, on a more symmetric definition, which also indicates what we should understand under the T-duality of Batalin-Volkovitsky theories or quantum L infinity algebras. Okay, so just very briefly tells you the direction where we go or what we try. Okay. So to understand the things, just think of linear version of this quantum odd symplectic category. So forget about manifolds. We are back to differential graded symplectic vector spaces, and also our Lagrangian subspaces, the correspondences or the relations, symplectic relations, whatever you prefer for the name, will be also linear spaces. And in this case, you can see that whenever you have such a Lagrangian submanifold here, it has a form which is a product form where you have two pieces which are both isotropic, one in M and one in N, respectively, and there you have a graph of some isomorphism. And this isomorphism goes from the symplectic pieces of M and N, which, since you have this isotropic eyes, well, of course, you can do symplectic reduction. So you take the orthogonal complements and you factor out, you get symplectic spaces. And well, it's an easy exercise to say that they must be isomorphic. Okay, so if you now use my definition I gave you before and use this specific form, which I said, I mean, it's always like that, this explicit expression for my Lagrangian subspace, I easily see that actually if I do this integral, I obtain an action, a semi-density on N. But now my action will actually depend not on the whole N, it will be just coming from a function on this symplectic piece. So I ended up in a subspace of my N. But of course, similarly, I can reverse the role of M and N, still keep the same Lagrangian subspace, and I can integrate the other way around. And my proposal for the definition is I should get the same up to this isomorphism. Remember, this Tm and Tn, these are isomorphic. So if I get my two actions related by this isomorphism, I would say my actions or my Batalin-Velkovisky theories or quantum L-infinity algebras are equivalent. So this is now completely symmetric, right? Okay, so maybe if I have still one minute. Oh, great, you are so kind. Okay, so this somehow suggests what the T-duality could be. So let's say I start with the, if I have two Batalin-Velkovisky theories, and I find some Batalin-Velkovisky theory on N, such that I obtain my M and M fiddle by symplectic reduction from my N. Well, this means that essentially these Lagrangian subspaces that they are given by the symplectic reduction. And so I would say that these two actions are T-dual if you know, integrating Sn with some semi-density supported on L, or integrating here with some semi-density supported on the middle. Well, if they are obtained in this way from an action, from a theory here on the top, then I would say that they are T-dual. I don't know if I'm saying something really wrong and you wouldn't like to call it T-duality, please tell me. I am ready to change the name to whatever is like. Okay, and maybe the very last remark. So if you have such T-dual action, that doesn't mean automatically that they are equivalent in the previous sense. What you can do, you can compare them on the intersection, because since these are reductions, so you can, turn this around and compose, and you get the Lagrangian here. Yes. And now I'm in the situation I was before. I can ask whether these actions here are equivalent in my previous sense, and well, for that, these integrations here and here have to be related by an isomorphism. So in this case, they will be also equivalent in the former sense. Okay, so just remark, you can of course now interpret everything in what I told you in terms of this homological perturbation lemma, because you have natural subspaces, these I's from the, for your Lagrangian subspaces, for your correspondences, which come, of course, from the fact that you have the differential. Okay, I guess that's all. Now, of course, to make it work for manifolds, there are some technical assumptions under which everything what I did applies on the level of the tangent space in every point, and I have to ensure that everything I defined, all the fibrations will be nice fibrations, will be foliations, etc. But well, I guess this is doable, and I don't know. I probably forgot something, but okay, I'm over anyway with my time. So thank you very much for your attention.
Thank you very much. Questions?
Sorry, how far do you actually get if you look at this from abstract nonsense perspective via cyclic operators or so with the definition of the morphisms? Or do you just get isomorphisms, or what happens there if you try to define the morphisms more abstractly as homotopy algebras or so?
Well, that was my proposal for the.
Right. That is what you're doing?
That's what they're doing.
That's exactly what you get from abstract nonsense.
Yeah, that's what I get from abstract nonsense.
Is there any other question? If not, we can thank our speaker again. Thank you. And we have last speaker of the morning session. So the speaker is Max Kurkov, going to talk about Poisson gauge models and Seiberg-Witten maps. Thank you. You can start.
Hello. Thank you for the introduction. Today, I'm going to present the recent results which we have obtained in collaboration with Patricia Vitalia and Vlad Kupriyanov. Oh. How do I use the laser pointer? Okay. This way. Okay. The results have not yet been published. However, they will come out quite soon. My talk is organized as follows. First of all, I will introduce the Poisson gauge theories, and I will tell you where these models come from. After that, I will present a technical overview of the construction. This construction exhibits a nice symplectic geometric interpretation. The most important result which we have obtained concerns the universal solution for an arbitrary non-commutativity of the Lie algebraic type. In the end of my talk, I will discuss the ambiguity of the construction. Okay, let's start. So the non-commutative deformations of the space-time may be characterized by the Kontsevich star product of functions on the space-time. For the discussion, I need an explicit expression for the Poisson bracket, which is defined by the Poisson bivector theta ij. So our final aim is to construct the non-commutative gauge theory requiring a compatibility of the gauge algebra with the space-time non-commutativity. In particular, the infinitesimal gauge transformations should close this non-commutative algebra. The star product enters in the game here. The commutative limit has to reproduce the standard abelian gauge transformations. Of course, such a problem is highly non-trivial. Therefore, we need some simplifications. So I will review the construction following the original article by Kupriyanov and Vitali. The first point is the simplification. So we impose the semi-classical approximation. In particular, the star commutators will be replaced by the imaginary unit times the Poisson brackets. In this approximation, the full non-commutative algebra of gauge transformations defines the Poisson gauge algebra. So I repeat the statement of the problem. One has to construct a gauge field theoretical model which has this algebra of infinitesimal gauge transformations. In the commutative limit, our gauge model must recover standard abelian gauge theory. We work at the classical level only. We don't quantize our theory. So if the Poisson bivector theta is constant, the required gauge transformation can be easily constructed in this way. This formula is simple and natural. However, if theta does depend on the coordinates, these naive gauge transformations do not close the Poisson gauge algebra. Therefore, we have to generalize this formula in some way. The solution is the following. For non-constant Poisson bivectors theta ij, the deformed gauge transformation can be defined as follows. In this formula, the components of the matrix gamma, which depend both on the gauge field A and on the coordinate x explicitly, these components have to satisfy the so-called first master equation. Apart from that, we require that in the commutative limit, the matrix gamma goes to the identity matrix. One can check by direct calculation that these gauge transformations indeed close the required non-commutative Poisson gauge algebra and exhibit the correct commutative limit. So far, we have constructed the deformed gauge transformations only. In order to construct the dynamics, we need the dynamical variables. The deformed field strength has to transform in a covariant way, in this way. Apart from that, we require that the deformed field strength has to reproduce correctly the commutative limit. The solution was obtained by Vlad Kupriyanov in the following form. This formula is quite complicated. It involves the matrix gamma, which we introduced before, and there is a novelty, the matrix rho. The components of the matrix rho have to satisfy the second master equation. And we also require that in the commutative limit, the matrix rho tends to the identity matrix. The last technical ingredient of the construction is the covariant derivative. We require that for any field psi which transforms in a covariant way upon the deformed gauge transformation, the covariant derivative has to transform properly. We also require that in the commutative limit, this gauge covariant derivative tends goes to the standard derivative. This expression was constructed by Priyanov. The formula is this one. As you can see, this formula involves all the ingredients which we introduced before: the matrix gamma, which satisfies the first master equation, and the matrix rho, which satisfies the second master equation. These deformed objects, so the deformed covariant derivative and the deformed field strength, allow to write down gauge covariant equations of motion. So the dynamics in this model is defined by this formula. As you can see, these equations are similar to the first pair of Maxwell equations. However, we substituted the standard field strength by the deformed field strength and the standard derivative by the gauge covariant derivative. Okay, though the construction may look too complicated, too artificial, it exhibits a nice symplectic geometric interpretation. The first part of the symplectic geometric interpretation was obtained by Kuprianov and Szabo. And the first ingredient of the construction is the symplectic embedding. We extend the Poisson structure from the basic manifold M to the cotangent bundle. I denote through Pj a local coordinate on the fibers. So we already have, starting from the beginning, the Poisson bracket between the two axes. One has to define the Poisson brackets between x's and p's. We assume that the Poisson bracket between p and p is 0. So let gamma be the Poisson bracket between x and p. So effectively, the matrix gamma defines the symplectic embedding. The second ingredient of the construction is the set of the constraints in this extended symplectic space. The constraints are these ones. Of course, the new symplectic structure must respect the Jacobi identity on the extended symplectic space. And this Jacobi identity on the extended symplectic space is exactly equivalent to the first master equation, which we introduced before. So, briefly speaking, the matrix gamma defines the symplectic embedding, and the first master equation for the matrix gamma is simply a Jacobi identity on the extended symplectic space. The deformed gauge transformation introduced before can be represented as a simple Poisson bracket on the extended symplectic space. Of course, after calculating of all the derivatives, we have to set all the constraints equal to 0. Fine, but the interpretation which I presented before says nothing about the matrix rho in this role. Me, Patricia, Vitaly, and Kuprianov discovered the role of the matrix rho in this symplectic geometric construction. So now I switch to our unpublished preprint. Performing a transformation in the basis of the constraints, we construct the new constraints in this way. Rho is some non-degenerate matrix which depends on both x's and pi's. In particular, the new constraints are equal to 0 if and only if the previous constraints are equal to 0. The important statement is the following: the deformed field strength and the deformed covariant derivative, which I introduced before, can be presented as simple Poisson bracket in the extended symplectic space. The deformed field strength is the Poisson bracket between the new constraints, and the deformed covariant derivative can be written as this Poisson bracket on the extended symplectic space. The gauge covariant condition for the deformed field strength is exactly equivalent to the second master equation for the matrix rho. So far, I discussed just the main points of the construction. So, as you can see, any gauge Poisson model is completely defined by the two matrices, gamma and rho, which satisfy the matrix equations, the two master equations. Okay, let's discuss some solutions. I will consider a class of Poisson bivectors which are linear in coordinates. The constants f, a, b, c satisfy the Jacobi identity. Therefore, these constants can be seen as the structure constants of a Lie algebra. For these reasons, I call this kind of non-commutativities the non-commutativities of the Lie algebraic type. Kupriyanov and Szabo obtained a special solution of the first master equation in terms of a single matrix-valued function, which is valid for all Poisson bivectors of the Lie algebraic type. This solution can be presented as follows. First, I define the matrix A hat in this way. As you can see, it is actually an element of the joint representation of the underlying Lie algebra. And the universal solution is given by this matrix-valued function, where G is this guy. Okay. The missing ingredient is the solution for the matrix rho. In our recent preprint, we demonstrated that also the second master equation exhibits the universal solution for rho expressed as a matrix-valued function of the same matrix variable A hat. The answer is given by this formula, and the two universal solutions for gamma and for rho exhibit these simple connections. The inverse rho equals to gamma minus I times A hat. And I repeat that using these universal solutions for gamma and rho, we can build the Poisson gauge model completely. We know both the gauge covariant equations of motion and the deformed gauge transformations which close the Poisson gauge algebra. Okay, let's discuss some example of this scheme. I will consider the Poisson bivector which corresponds to the generalized Kappa-Minkowski non-commutativity. It is defined in this way. Omega j is some constant vector. If just omega 0 is different from 0, it will be the standard Kappa-Minkowski non-commutativity. But for we prefer to discuss consider a more general structure. Inserting these structure constants in our formulas for the universal solutions and calculating the matrix valued functions, we obtained these explicit formulas for the universal solutions for gamma and rho. Okay, but what about other solutions? Of course, when you solve differential equations, you can obtain different solutions. So now I want to discuss the arbitrariness of this construction. In particular, the solution for gamma, which I presented before, is different from the solution for gamma for the same Kappa-Minkowski non-commutativity, which we found with Kupriyanov and Vitalia 1 year ago using different techniques. Also the solution for rho, which comes out from our universal solutions, differs from the solution for rho obtained in the previous studies. So is it just an ambiguity, or there is something deeper behind? The answer is there is something. Okay, a few general statements. First of all, for any invertible field redefinition, this one, we can construct the new matrices gamma and the new and rho, which again solve the master equations. So A tilde denote the new fields, A denote the original fields. Of course, these matrices gamma tilde and rho tilde define one more Poisson model for the same Poisson bivector theta. The new model has new infinitesimal gauge transformations. The main observation is the following. Upon this field redefinition, the gauge orbits are mapped onto the gauge orbits. Therefore, the invertible field redefinition can be seen as the Seiberg-Witten map between the two models. I use the terminology Seiberg-Witten map exactly in this sense. So we constructed two different Poisson models for the same non-commutativity. However, the gauge orbits of one model are mapped on the gauge models on the second model. In particular, the universal solutions for the Kappa-Minkowski case are connected with the universal solutions which we obtained in the previous studies by this invertible redefinition of fields, by this Seiberg-Witten map. Okay, let us summarize our findings. First of all, I presented a review of the Poisson gauge models. I stress that these models are completely defined by the two matrices gamma and rho, which solve the two master equations. The second point is the fact that these models exhibit a nice symplectic geometric interpretation. In particular, this symplectic geometric interpretation is based on two ingredients: on the symplectic embedding and on the set of the constraints in the extended symplectic space. The role of the matrix, the matrix gamma defines the symplectic embeddings. The matrix rho shuffles the constraints in this extended symplectic space. The most important result which we have obtained is the universal solution of the second master equation, which is valid for any non-commutativity of the Lie algebraic type. If we combine this universal solution for the matrix rho with the universal solution for the matrix gamma, which was obtained before, we can build Poisson gauge model for an arbitrary non-commutativity of the Lie algebraic type. And the last discussion concerns the arbitrariness in this construction. We have seen that invertible field redefinitions give rise to new solutions of the master equations. However, all the outcoming Poisson gauge models are connected with each other through Seiberg-Witten maps. How much time do I have? 2 minutes. Okay. Then I stop here. Thank you for your attention.
Thank you, Max. Questions on there?
You showed the gauge covariant equations of motion, right?
Yes.
Now, can you obtain them from an action?
Of course. And that's why I asked if I still have 2 minutes. Yeah. So, bonus number 1, comments on the Lagrangian formulation. Since we have the gauge covariant field strength, we can also define the gauge covariant Lagrangian. The tricky point is the following. The Poisson bracket is not necessarily a total derivative. Therefore, in order to construct the gauge invariant classical action, we have to multiply this Lagrangian by some weight function mu, which solves this partial differential equation. So the gauge covariant action is given by this object. The gauge invariant action is given by this object. And one may wonder whether the outcoming classical equations of motion are the same as we introduced before or no. The tricky point is the following. The equations of motion that we introduced before are non-Lagrangian. However, if this condition is satisfied at mu equals to 1, so we actually need not to introduce any weight function. The Euler-Lagrange equations of motion are exactly equivalent to the natural equations of motion which I introduced before. In particular, the left-hand side of the Euler-Lagrange equations of motion can be obtained by from the natural equations of motion multiplying by the matrix rho. If this condition is not satisfied, the Euler-Lagrange equations which come out from here contain this quantity mu. Did I answer your question?
So the bottom line is that you can obtain them from
Yes.
a Lagrangian in some cases.
Yeah, or if this factor mu is fine for you, in all cases. Because as far as I know, also in other approaches to non-commutative gauge theories, when people introduce by hand star product in the classical action, they do introduce this measure mu in the Kaplan-Minkowski case.
We have a question here, there, and then there.
Oh. Too many questions, huh?
Okay, thank you. I just wanted to point out, so basically, as far as I understood, you want to define a non-commutative gauge theory on some whatever generic Poisson manifold. And there is a very simple, rather general way to do this, which I have somehow explained many times, but people don't listen. It's you need to find, you just need to find harmonic coordinates on this Poisson manifold in a certain sense, which I can explain here. And then these are solutions of Young-Mills type matrix models or Poisson, whatever you like. And this defines it for free a non-commutative gauge theory. It seems, okay, I'm not completely sure about your intention. Maybe it's a little bit different. I'm just saying it's a rather general story. You can easily define non-commutative gauge theories on rather generic class of non-commutative spaces. And it's much simpler than.
Well, I believe if you're able to do so, you will just solve these master equations in some other way. And I have a doubt that your harmonic coordinates are defined globally. This is another point, so that your transformation here all is defined globally.
But I'm just saying such things have been discussed long ago.
Actually, I had a discussion with Vlad Kupriyanov on that, on a similar issue, and the crucial point is the fact that more likely your transformation will not be globally invertible and will not be globally defined.
So I have a question concerning the gauge group. So this is U1, is it correct or no?
The deformed theory is U1.
Okay, so can you generalize this to a non-abelian?
This is a good question. Actually, one has to think about. So far, we didn't try, but this can be done in the future.
Okay, and I have another question. If you can go to the page 15, where you have solutions of the Seiberg-Witten map. So in your
in this part,
in this example, so omega is can be thought as a deformation parameter.
Exactly.
Yes, and your gauge transformations are restricted to be linear in omega, correct? Because you work with a Poisson gauge.
No, I would say they are not linear in omega. The only thing that they tend to the identity when omega tends to 0.
No, the solutions are for sure not linear in omega, but you start with restricting your gauge transformation to be Poisson.
Well, look, this is an important observation. These gauge transformations are non-linear in A, and they are non-linear in omega. In particular, introducing the non-commutativity in the game, you, by the end of the day, get non-linear dynamics. Your equations of motion and everything is in gauge transformations are highly non-linear in
I was just worried if it's consistent to have things that are higher order in omega and so on. Okay.
So the only linear thing in omega is the Poisson bivector.
Okay, thanks.
There was a question by Paolo.
Yes, I would like to come back to, I think, the question on the existence of the action. And I was wondering whether the measures that you introduced, the weight you introduced, if you can solve that equation, because it seems a differential equation that...
Well, for the Kaplan-Minkowski case, this equation has been solved. We have obtained a general solution of this equation in the article which I mentioned, where I said we had got all solutions. We solved this equation. Yeah.
Okay.
So it's true. This is true that we did not study a general solution of this equation for arbitrary theta. But when I say that we were able to define the dynamics, of course, I intended the natural equations of motion. So these ones we can write always. Yeah.
And the other very related question is, if you don't have the action principle, have you checked independently the integrability of your equations of motions that are well defined in other terms?
You mean if you were able to solve them? So far, no.
Okay, thank you.
Last question.
So the majority of questions about the bonus, so also about the bonus. So I just wondering that measure. I think you know we introduced this like gauge theory of star product or something like that. I mean, so and we also needed measure. So that measure came from some trivial requirement that the action is actually a trace. Action, the integral is a trace.
Yes.
So the same thing, right?
Exactly. And also this equation for the measure is identically the same, which appears in that old articles.
And then you can kind of like induce Seiberg-Witten map requiring you can introduce actually gauge transformation, kind of like transformation of a star, or you can like introduce gauge transformation. I mean gauge field, or you can treat it as a change in the star. Actually, I mean, so I think it's very similar to that. I mean,
well, one has to think about that.
Yeah. Okay. Thanks.
Okay. I think there are no more questions. Let's thank Max again. And the morning session is over. See you after lunch.